Thank you very much. So I assume you have the whiteboard, right?
Yeah, we can see it. Looks good.
Sorry, just a moment. Let me see if I can minimize. Okay. And you're just saying what I'm drawing, like this curve.
Yeah, yeah,
Okay.
looks good.
So I start the lecture. So first of all, we're going to just a few notes. First of all, I'm going to just make it a little bit interactive. So whenever you want to just say something, or you could just interrupt me and uh, say whenever you're comfortable. Furthermore, I'm going to first digress a little bit, somehow introduce the notation I'm going to use today, and then I'll get back to the main topic soon. So in mathematics, it quite happens that we've got some sort of entity, some sorts of objects, and we have some maps between them, just like the diagrams we drew in 240. For example, you could have just vector spaces over R. Your objects are just vector spaces, and your maps would just be linear maps, or some simpler structures, just for example, just merely sets and just functions between them. Or maybe even, for example, one could just consider their objects just all open intervals of R and consider its functions like from I to J as just all linear, sorry, as just all continuous maps taking I to J. So the good thing here is just this structure we are speaking of is quite simple. It's just some dots as our objects and some arrows, which is so general that it could be applied to various structures, various objects, and various, let's say, relevant maps. Because of its simplicity, it's sometimes actually worthy to focus on this diagram we are drawing and to see what structures can be made by just looking at the diagram. For example, one thing we could do is if we have some, let's say, some universe or some objects, we could just fix an object A here and wonder how does this object A see any other object B? That is, for example, what would be the set of maps, of course, relevant to the universe we're speaking of, from A to B. So let's give some examples. If we're taking our sets and we fix our object A to be just the set on one element. For each set B, what would be the set of functions from A to B? Where just A is just the one element set. So, any ideas? So,
What's the
yeah.
question again?
Okay, so what I'm saying is we can sometimes fix some object A, like here, and wonder for each another object B, what is the set of all relevant functions from A to B? For example, in this particular case, I'm thinking about sets. I fix A to be the set on one element, right? It's just one element. Let it just be nothing more concrete, like zero. So I'm asking for each object B, or each set B, what would be the set of functions from this one element set A to B? This one.
Is it like the functions that go from so it maps that one element to a single element in B, and then every element in B is every function.
Exactly. So just it's all those functions mapping this zero to each object to each element B. So it would just roughly be B itself, right? Or if, for example, I give another example, we could just make it a set on two elements. And again, this would just be B to the power of 2, right? Or if we're focusing on vector spaces on some particular field F, I'm fixing the F here because a linear map between two vector spaces of different fields is not quite relevant. So if I fix my A to be the field itself, what would the set of linear maps, from this F to any vector space V? So again, just like in this example, just need to just decide on what we want to take 1 to. So it would just essentially be V itself. So this is one kind of construction. The other way to look at it is like the opposite. This time, we fix an object A, and for each object B, we wonder what would be the set of, let's say, maps from this B to A. For example, if this is just sets, and I let A to be the set consisting of 0 and 1, what would the set of functions from each B to A, roughly?
Are these like the indicator functions where it's like either 0 or 1 for each element?
Yes, or in
In B.
some, sorry?
In B.
Yeah, and in some other sense, it would just be the power set of B. I just choose which subset I want to take to 0, and then I can just form a very natural bijection between this set and the power set of B. So the same thing is thought of vector spaces. If I fix my, let's say, object as vector spaces over F, and I fix my A object as the field itself, one might want to ask what would be the set of linear functions from any vector space to the field itself. So these notions turn out to be very important and very actually somehow exciting, so that we just call it a name, and we call this structure the dual space. The dual space of V. That is, the dual space is just the list of linear functions from V to F, and we denote it by V star. And in part, we call the elements of V star as linear functionals. So each functional is just essentially a linear map from from V to F. So yeah. So let's just figure out what this V star looks like. And the first thing one could ask is just what would the dimension of V star be? So if I have got a V here and I know this dimension, can I say anything about the dimension of V star? And for simplicity, let's just first assume that V is finite dimensional. So what would the dimension of V star be?
Is it the dimension of V?
Exactly, because know that this is n-dimensional, this is one-dimensional. So we know that this space would be n times one dimensional. So just you know that V star is n dimensional as well. So that's a great thing. We know that the dual space, the dimension of dual space, is just the dimension of V. So since they are of the same dimension, then naturally we could just create an isomorphism from this V to this V star, right? Because they have the same dimension. So now I'm going to do so. I'm just going to find an isomorphism from this V to V star. So how can I construct it? If I just call it like I, how should I define this I to form an isomorphism? And for example, what ideas should I just first think of when I'm going to construct an isomorphism between this V and V star? So one thing I could do here, you know that each linear map is uniquely determined by let's say the values on the basis. That is, if for each vi of the basis, I choose what this vi would be, then I have a unique linear map from v to v star. So I fix a basis here. Let it just be b, and for each vi, I want to just define a linear functional such that can have some hope that it in fact forms an isomorphism. One idea could be to define this linear functional, I call it vi star, such that vi star for vi is 1 and vi star for each other vj is 0. So that is like the ith coordinate of each vector. So I have now defined a linear function between these two spaces, and what I want to see is that if there is an isomorphism. So to be an isomorphism, it should first be injective. Let's see if it is injective. That is, let's see if for some ci vi star equals 0, that is like, yes, and sorry, we don't know yet. We just define this vi star and just need to find out whether it's a basis. That's what we're going to prove here. So now what we're going to do is just to see whether they are linearly independent. So we have some ci vi star, the sum is equal to 0, and I want to just check that whether we can prove each ci is 0 itself. So what are some ideas? How can I just prove it in this case?
So a suggestion for the people thinking is to think about, the CIVI star. What kind of object is it? And what does it mean for this object to be 0? So what is 0 in this, in this target space?
Sorry, just to confirm, vi star, it's a function when such that when you apply the ith element of the basis like v, you get 1, but if you apply any other basis element, you get 0, right?
Yeah, exactly. That's like the ith coordinate of each vector.
Oh, okay. So then when you apply like a general v, like depending, you'll get like either a sum of ones or yeah, something like that, right? It will be a
So
sum of ones.
your suggestion is to apply some v here to both sides?
Well, I'm just asking, like, if you apply, like, let's say, actually, I got it. I got it. Okay, thank you.
Okay, thanks. So what can I apply here, for example, to both sides to get something good?
What if we know that any vector can be expressed as a basis of v,
Hmm?
and so that's why like for every vector then functional would like give you either 1 or 0 depending on if the like certain vi is in the linear combination of a certain vector, and that's basically it, I guess. No.
Sorry, I didn't quite understand.
So we know that every vector can be expressed as a linear combination of the basis of v, right?
Right?
And so we know like vi star is a like functional, right? And
Right?
it is linear. It is a linear map, right?
Very sorry, yes, it's linear map. Because I defined a base
Yeah.
basis. Yes.
So for like if for example vi is in the linear combination of v, the function would give us 1 because like if we like expand it, that would mean like 1 times the like coefficient of vi in the linear combination. And so to be that thing 0, the coefficients like ci should be all to be equal to 0, I guess. Something like that.
So did I get you right? So is your idea to just apply both sides to vi? So someone vk, for example?
Yeah.
Okay, so exactly. So we do so. Uh, right hand side would just be 0 of vk, typically 0. The left hand side would just turn out to be ck, vk star of vk, because for all other terms, vi star of vk is 0, which is just ck. So we know that ck equals 0, so all c's are 0. So basically, these are all linearly independent. And as we have already proven that the whole dimension is n, we have n vectors linearly independent, so they must be a basis. So what we wanted to prove is now proven. We have proven that these vi stars form a basis of our dual space if v is finite dimensional. However, sadly, if is otherwise, if V is not finite dimensional, then the dimension of V star is not even necessarily equal to the dimension of V. There could be some cases when this V star is not of the same dimension of V. So although it works pretty well for finite dimensional ones, for infinite dimensional vector spaces, these VIs are still linearly independent because here we had no assumption of it being finite dimensional, but they might not necessarily actually form a basis anymore. That's why we focus the whole theory here to just finite dimensional vector spaces. Now, the VIs we constructed, the VI stars we constructed based on this VI are called a dual basis. So for each basis B consisting of VIs, we define the dual basis of all these VI stars, and then there was isomorphism linking to each element of V to each element of V star. The only thing is, this isomorphism is heavily based on the basis we choose. If we choose a different basis, we get a different isomorphism. So that's not really what we're looking for. We're looking for some natural, logical isomorphism, which is independent of the basis we choose for our computations. However, unfortunately, it is somehow roughly provable that there is no natural isomorphism between these two. However, in some special cases, we might have an extra structure, and you might be able to form a new isomorphism based on this structure we have. In particular, if our vector space is equipped with a bilinear map from V times V to F, and bilinear maps are maps which are linear in each of their elements. For example, lambda of V1 plus V2 of U equals plus lambda of V2 U, lambda of C V and U equals C lambda V and U, lambda of V U1 plus U2 equals lambda of VU1 plus lambda of V and U2, and finally lambda of V and CU equals C lambda of V and U2. That's the bilinear map. You have seen bilinear maps in high school. For example, for the R2 space, the dot product defined between two vectors, in the sense that if V equals AB and U equals CD, we define V dot U as AC plus BD. Kind of observe that is exactly a bilinear map here. So sometimes our vector space is equated with a bilinear map with the property that for each V, lambda of V and V is not 0 if V is not 0. For example, does dot product in R2 satisfy this condition? If a vector and V dot V equals 0, then we know that, for example, V is 0 in particular. So if you're given such a bilinear map, then you could find an isomorphism between V and V star such that for each V, you assign the linear functional obtained by fixing the second term as V. That is lambda of dash V of U would just equal to lambda of U times V. So as we fix the second term, and since it's bilinear, it's in particular linear on the first term, then you get the bilinear map. Obviously, this is linear functional, and since the whole thing is actually linear in the second term, you can also see that this T here is also a linear transformation between V and V star. So just the thing is to just check that whether it is a bijection, whether there is an isomorphism. To do so, we'll check it whether it's injective. If it's not injective, then there is some V that lambda of U and V equals 0 for each U in V. So typically, we can just plug in V in this case, lambda of V and V equals 0. So by the condition we had earlier, you know that V must be equal to 0, and so our linear transformation is an injection. And again, since we have already proven that V star is n-dimensional in injection isomorphism, and we have found an isomorphism completely based on the lambda we are given, which is normal, it is often just a quite sensible and natural bilinear map in our vector space. So basically that's it.
Yeah, sorry, let me just make a small comment. Can we go back
Sure.
to the previous slide for a second? I don't know if they're saved or not. But the idea behind this is that, okay, so you can go to the, here we've been presented with two ways of how to relate the original vector space with its dual space, right? So the first case, it really depends on the choice of basis, right? You choose a basis for the vector space, and then you get a natural choice of dual basis, right? And so this way you get a map from V to V star. The problem is this map really depends on the choice of basis. Like you can check that if you chose some different basis, the map would map the same vector to a different linear functional, depending on the choice of basis you have. Okay, but then in the second case, we said, okay, suppose we had like a really particular kind of function, and that defines a different map for us from V to V star. And in quantum mechanics, it turns out we will precisely have this second scenario, where we will have some kind of bilinear map, so a map that takes in two vectors, outputs a number. Well, it's not going to be bilinear, it's going to be skew linear, or whatever the terminology is. But the point is, you're going to have a map kind of like that one, and then that will give us a relation of that map to a natural relation between the vector space and its dual space. And this map is going to tell us something physical, and it's going to be interesting for that reason. That's one thing. And and then the other thing is we're going to realize that actually, maybe there will be some physics in this dual space a little bit, or something that will be helpful that will be in the dual space, but not in the original space. And the other thing is, not just in quantum mechanics, but in classical mechanics, there's a way to formulate classical mechanics through kind of this similar idea of you have vectors, and then you have linear functionals, and then you have some kind of bilinear map, and it relates the linear functionals to the vectors. And roughly the idea there is that you have some kind of linear functional, which you get in some way from the energy function, and then you use this map to go from this thing that we got from the energy to get a vector field on our space and have some differential equations that follow this vector field. Okay, but essentially this idea is quite central it appears in a lot of places that you can, given a bilinear form, you can relate the vector space to the dual space. Okay, that's not very useful words that I said, but okay, I said them. Go ahead.
Not very much. So far, we have just defined a transformation taking vector spaces, right? So that's what we have so far. We take objects, we produce objects, and this is by just taking the dual of our vector space. However, this transformation would be the most useful if we can not only take objects to objects, but we can somehow take linear maps to linear maps as well. So that is, if we have a linear map between V and W, then it should be a quite natural agenda to try to find a similar linear map relating V star and W star in some sense. Sadly, the thing is, there is no natural angled linear map between this V star and W star. We cannot do so. However, there turns out to be a very good way to construct a linear map, taking W star to V star instead. So that's somehow some part of the dualism. We, in this case, reverse the direction of our linear maps, which happen turns out to be quite the case in mathematics when we're taking some objects and some transformation to some other object and transformations. So let's just construct this T star. Typically, we should assign for each psi, where psi is a linear functional in W, a linear functional in V. So in other words, here we have V, we have W, we have this psi from W to F, and again, of course, we do have this T assumption, and we're just going to try to compute and construct a linear map from V to F based on psi and T. So what is a good idea here? What can we do, for example? Any ideas? So, okay, in fact, it quite follows from the diagram we have here. Let's just compose these two maps, and you just give us a linear map from V to F, right? So we might want to define for each psi T star of psi as just merely psi O T. And clearly, this is first a linear functional because, of course, it's just the composition of two linear maps. And one could also check that this transformation is a linear map between W star and V star. That is, for example, T star of psi 1 plus psi 2 is psi 1 plus psi 2 OT, which is merely T star of, sorry, psi 1 plus psi 2. So, yeah. And we call this T star as the dual map of T. So again, let's just, now that we have constructed our dual map, let's just try to analyze this map and just to see how it relates to the original map T. So in particular, let's just see if we can find a good matrix for T star. And maybe just if we can compare this matrix to a matrix of T. So if we have a matrix of T, we call A, and naturally it should just be based on a basis of V and a basis of B W. So let me just number them by B1 and B2. B1 is a basis of V. B2 is a basis of W. We form a matrix A prime of T star based on two bases from V star and W star. So typically, we might want to just choose a random basis, want to just be related to B1 and B2. So let's just here put the dual basis. Let's just put B2 star here and B1 star here. And let's just see how it looks. So to compute our matrix A prime, we can compute, for example, in particular, each column. To compute each column, we can just look at A star of the ith element of the first basis, that is psi, or maybe we can just say Wi star. and it should be expressible as a linear combination, or just denote them by B. It's a linear combination of the dual basis of V star, right? So I'm going to find these BKIs. What should I do? What are some ideas to compute just these coefficients? Say I want to compute BJI. What can I do? So again, I can just plug in Vj on both sides because we have seen before that if I just apply this linear functional here on Vj, then all Vk stars would be 0 and Bji, the desired coefficient, would just come out. So I compute T star of Wi star of Vj, which would just by definition be the W star, Wi star of T of V. So by the definition, we know that this would be Wi star of sigma, let's say L from 1 to M of B L, sorry, A, where these A's are just they're just let's say elements of this matrix A. A, L, J, Wi by assumption, which would just be A, that is L, would just be L, I, J, right? So this is what our BJI would be. So we have proven that, interestingly, BJI just equals IJI for each I and J. This should strike us as very familiar. We have seen this before. This is exactly how we define the transpose matrix. Just the way that we define the transpose matrix, such that each element, be it Ji is just Bij, we have it here, right? So a striking fact here is that the matrix of the dual map with respect to the dual basis is just the transpose of the original matrix with respect to the original basis. And here, transpose. So we have found, let's say, another representation, another interpretation of the concept of transpose. It could just be thought of as the matrix, as the relevant matrix of the dual map. So now that we have figured out what our
Well, I
matrix is,
think you should pause for a second.
right?
Maybe wait for a question or something like this.
Okay. So any questions so far?
Yes. Give it a moment.
Sure. Thank you.
Right. So, in that case, I'll just make a comment that what's really important about this fact is that so here we chose a basis, right? And we got that we chose a basis for V. That gave us a naturally linked basis for V star, and we got that the matrix in the basis from V to W is the transpose of the matrix of T star going from W star to V star. right? But note once again that T star itself, we did not have to pick a basis anywhere for defining T star, right? This was just a calculation of a matrix in a particular basis, but overall T star is well defined without any choice of basis.
Right.
Okay. Yeah. Okay. Go ahead.
So thanks. So now that we have just found out what the matrix is, let's just see if we can just compute the rank nullity of T star. So our goal here is to calculate the rank of T star and also the nullity of T star. So just focus on rank here. We already know that for each matrix, so for each linear map T, if A is a matrix relevant to T, then just rank of T would just be the dimension of the span of the all columns of the matrix A, right? This is A. It would just be the dimension of the span of these. We know it's around 240. And we in fact know that we can just find an A here. Let's just call it A prime. This A prime, we could choose a basis so that it is just the transpose for some matrix of T, and therefore, for that matrix, it would just be, if this is A, it would be the dimension of this span of the rows of A, right? This is what the dimension and the rank of T star would be. So basically, for a matrix of T, the rank of T star is just the row rank of A. But yet we know nothing about what the row rank of A is. Sure, we know that the column rank is just the rank of T, but we don't know yet what the row rank is. So this method doesn't work. We have to appeal to some other method. Another method is to just appeal to rank nullity, and we know that rank of T star is M minus the nullity of T star, where M is just the dimension of W, right? Which is just a dimension of W star. So what we should do here is just to instead focus on the nullity of T star, because it seems much more it seems much simpler for a linear functional to be the kernel of T star. It's just a lot more comprehensible than it to be just either image of T star. So let's just see what the kernel of it is. By the definition, the kernel of T star would be all linear functionals psi such that psi OT equals 0 by definition. So let's just see what this interpretation means. What does it mean that for a linear functional for its composition with T is to become the zero linear functional. Let's see how it happens. In fact, if we have like this phi and this W, we have this T taking V to W, right? And we want to find all those linear functionals taking everything in T that is like the image of T to 0. That is, the kernel of psi should be a superset of the image of T. Right? This concept actually introduces a very new notation and a very important one, which is the annihilator. That is, for if V is a finite dimensional vector space, for each subspace of V, we define the annihilator just be all linear functionals such that they are completely zero. Sorry, they're completely zero on the subspace U. So basically, that psi of ours is in the kernel, find only if it's in the annihilator of the image. So since we wanted to know the dimension of the kernel, we want to know the dimension of the annihilator. So if we can find a method to calculate the dimension of this U star, sorry, then we can have our problem solved. So how should we do this? How should we just find the dimension
Yeah.
of this U
Sorry,
star?
could you stop for a second and rewrite what was the result on the previous page that we got, that the kernel of what was equal to what?
Okay,
Just for a second. And then Archid had a question.
sure. So we wanted to find all psi's, such as psi OT, just drawing a line here, equals 0. That is, if you have V here, and we have this W here, T taking elements from V to W, want to find all those psi's such that psi is 0 on every element taken from V. That is, if T takes all elements of V to its image, we want psi to be 0 on all elements in the image of T, which is just typically a subspace of W. So just the kernel, if this is the kernel of psi, that's what we want. And for example, if just T is surjective, then typically we would have to only let psi to be 0. Or for example, if otherwise if T is just a 0 map, taking all elements to 0, then psi could just be every element it wanted to be. It could have been anything. So, may I proceed?
Sorry, you said that the kernel of T star is a subset of what was?
What I said is, do you mean this line?
No, on the previous page there was.
I erased it, so maybe can you just recall what it was?
But that's my question, what it was. It was like kernel T star is a subset of something, and I did not catch it.
Okay, so we want to just calculate the dimension of this thing, right? And we just use the definition. For a psi here to be in the kernel, that is, we should have T star of psi, it should equal to 0, which is by definition psi OT. Is that okay right now?
Yeah.
Okay, so if there's any other questions, I proceed. So, okay. So we're about to calculate the dimension of this U star. And to just do so, a natural thing is to just again apply to basis and see if we can just calculate the dimension based on the basis of V and U and stuff like that. So we choose a basis for V. And since we know that U is a subspace of V, we can just choose some basis V1 to Vk. These are all bases for U, and we can extend it to a basis for V, right? So the first k elements form a basis of U, we extend it to a basis of V. Is that clear? Okay. So now again, we consider dual basis because why not? And we want to find all linear functionals constructible from these dual bases such that U is 0 on all of U. So what are some examples? What are some vectors? What are some linear functionals that I'm sure are certainly in the annihilator? Just some examples. I mean, typically, for example, the zero vector is. Any other vectors I can be sure of? So clearly, each vi star for I bigger than k is in the annihilator. Because of course, all the elements of U have their coefficient of vi0 because they're only just constructed from v1 and vk. So each vi star is in U for I bigger than k. Obviously, their span is also in U annihilator. So the whole subspace spans by vk plus 1 up to vn star is in the annihilator. Now, could there be any other vectors, any other linear functionals in the annihilator? Any ideas? Okay, so let's see. If a linear function,
Hold on. Give people another moment to
okay,
think. We still have time. It's okay. No
okay,
rush.
sure.
Maybe repeat the question.
So my question is, we wanted to just find out what vectors are in the annihilator. We figured out that all vi stars for I bigger than k, they are all in the annihilator, and typically the span of these things are also in the annihilator. So you're just going to find out whether there are any other vectors or not. So there's a comment apparently. Let me just see. Okay. So I don't have access to the comments, I think.
I was
Maybe
just
you
saying
could.
that like I think that these are actually equal. Like I think anything in the annihilator has to be in the span of VK plus 1 all the way to star.
So that's a good guess, but how we can prove it? How can we prove it?
Well, you have this inequality, and then I think you could take an arbitrary element in the annihilator, and then it's in the annihilator. I have to think about it, but yeah, that's what my first step would be take an arbitrary element in the annihilator, and then try to show that it can be spanned by
Okay.
some vectors in there.
So we have an element in the annihilator.
So I think my general advice is, if you're not sure how to proceed, with showing that something is something, you should write out the definition of what it means to be that something. And then usually what to do becomes completely obvious.
Right. So we have this in annihilator that is phi of u equals 0 for each u in the subspace u, and of course we can just appeal to our basis another time and assume that phi is the sigma ai vi star for some ai's. So any ideas?
Can you can you remind us what U was again?
Okay, so U was just our subspace. U was a subspace. This U is just the subspace of V for which we want to compute the annihilator, as I mentioned.
Could you apply like a U? Sorry. Like you apply it to both sides, and then this one, the first VK are linearly independent. So the only way that, and then the last ones are all zero. Then the only way those could all sum zero is if like they could be spanned by just the VK plus one to Vn star.
So you apply to some VI such that I is smaller than or equal to K, right?
Yeah.
Exactly. So clearly this VI is in this U. So we have this condition. We should have sigma AI VI star on V, let's say J, should be 0, which is in fact just AJ. So this AJ is 0. Therefore, everything here is just expressible as a linear combination of these VI stars from K plus 1 to N, which is just in fact this span we've argued earlier. So basically, we've just proven that this annihilator is just the span of the dual basis of our extension, since there are just n minus k basis elements. Then of course the dimension of u star, so u 0 would be just n minus k. So we figured out a very big important thing. The dimension of the annihilator, the dimension of the whole space, minus the dimension of the subspace. So, okay, let's get back to our original problem. We said that the rank of T star is m minus the nullity of T star. The nullity of T star was by definition the dimension of the, let's say, kernel of T star, which was the dimension of the annihilator of the image of T, which is, by our new lemma, just m minus the dimension of the image of T, which is just basically just m minus rank T. So combining these two results together, we just find out rank of T star is just the rank of T. That's, I think, a very important result. However, let's just not forget what you said earlier. Earlier, in a failed attempt to compute the rank of T star, we noticed that if A is like a matrix of T, then the rank of T star would just be the span of the rows of this matrix A, right? This would be the rank of T star. That is the row rank of T. On the other hand, we also knew from earlier that the dimension of this span of the columns is just the rank of T itself. Now we have figured out that these two quantities are equal. So we have figured out that for each matrix, the row rank is equal to the column rank, which is a result that we did not prove in 241. It just turns out that these two concepts are equal, and we can just assign a single value of rank to each matrix. And yeah, that's it. So I think that's everything.
Yes. So let me that's good. I just want to try and do like a little concluding remark and draw a bit of a picture. Let me see if I can remember how to
So let me
draw
just turn
this.
off the whiteboard.
No,
Okay.
can you bring back the whiteboard, or is
Oh
this
yeah.
okay? I just wanted to draw on the same one.
Right. So let's see if I can just, okay. Yeah.
Because every time I do a whiteboard, it doesn't work for some reason. I don't know why. Okay, so I'll just draw a little bit of a picture. Let's see. Where can I do, sorry. I just want to have a option to do more colors. Okay, there we go. So let's do, okay. So we had, nope. Sorry. Let me just clear my drawings. Okay, black. Okay, perfect. So we had our vector space V, right? And then we had a map going from V to some other vector space W. Okay? And then we had a linear functionals phi, right? And this was our map T. Do you agree? And then we had a map on linear functionals, which would take a linear functional on W and turn it into a linear functional on V. So all it did is it would take phi and just pre-compose it with T. So it would kind of take phi and pull it back to start on V. Do you agree? Yes? Okay. And so what did we realize? So we wanted to study this map T star. So naturally, we wanted to understand what is its kernel and what is its image. Okay, and how does that relate to T? So what we realized is, suppose, right? So what I have to do is I have, I take phi, and then I plug in vectors into phi that came from V using T. Do you agree? So suppose we looked at phi, and let me just switch colors here. And suppose, this part of, whoops. Can I undo that? Okay, suppose that this part of the vector space was the kernel of phi. So this part of the vector space was sent to 0 by phi. And so then, in some sense, the other part of the vector space was sent to something non-zero. Okay. Well, let's see what needs to happen for phi to be sent to 0 by t star. So this is a question to everybody else. This is just the one point that I want people to really understand, because this is the crux of the whole thing. So suppose this part is the part that phi sends to 0, right? So under what condition does t star, so precomposing phi with t, send phi to the 0 linear functional? What needs to happen? So Fyodor or Aimantas, because I guess the other people have already answered quite a bit of questions. Or Alisher, I think he's joined us later too. Right, so what needs to be true about t such that this particular functional gets sent to 0 by t star? Right? So it means that any vector v I plug into phi composed with t gets sent to 0. What needs to happen? Any thoughts? Oh, whoops. Fyodor or Aimantas? Like just suppose I just unmute and then just say whatever comes to your mind, right? Like what is t star phi, right? I take in a vector in V and then I plug it into what? First.
T.
Into T, and then I plug the result of that into
The functional.
into phi. Yes. So now I'm saying that I want that to be 0 for any V I plug into it. Right?
Yes.
So what has to happen
Oh,
for that to work out?
wait. Can just T be like a map to just 0? No?
Okay, T could be a map to 0, but but that's too specific, right?
Okay.
I want, suppose I fix a functional phi, I have a fixed functional phi. What has to be true about T for T star phi to be 0? This means that, okay, I plug in a vector V, I get what? I get TV, right? And then for that to be sent to 0, what has to be true? Look at the diagram I drew, and there's this diagram has only like 3 things in it, and one of those things has to be the answer. It's even in a different color from everything else.
TV's in the kernel of phi.
That's exactly right. So, if the image of TV is contained in the kernel of phi, then T star phi gets sent to 0. Right? Phi gets sent to 0 by T star. Do you agree? Okay.
Yeah.
And so, for...
Wait, could you write that out?
Yes. So, if the image of T is contained in the kernel of phi, then T star of phi is 0. Because I plug in any vector V into T, and then TV is then inside of the kernel of phi, because the image of T is in the kernel of phi. And so then if I do phi composed with that, then I always get 0. Do you agree? So that's why we define this thing called the annihilator, right, of a subspace. So the annihilator of a subspace was all of the linear functionals which have that subspace as part of its kernel. Do you agree? So the annihilator was all the linear functionals that send a certain subspace to 0. So this is a bit annoying because my thing is a bit broken, but if I have a certain subspace U, right, then the annihilator of the subspace is all of the linear functionals that send U they send at least U to 0, and everything else, okay, it can do whatever. Okay? And that's good. And so then we realized that, okay, what did we prove? We proved that the rank of T star is the same as the rank of T, right? So what did this mean? We realized that, so suppose T has some image, Let me draw this. Actually, I'll just erase everything right now. Clear all drawings. Does this work? That just did nothing. Clear my drawings. That also did nothing. Okay, most amazing Zoom experience with me. Good. So I'll just draw. Oh, thank you. Okay, so I'll just draw. Clear everything. Good. So I'll just draw this again. So suppose, okay, I have this, and suppose I have T, and suppose T maps into this section, this part of the vector space. So this is the image of T. Yeah, that's good. This is the image of T. Do you agree? So then, what we want to look at now is see, okay, which linear functionals get sent to something non-zero. Right? So we know that linear functionals which have their kernels which the kernels of which contain. So we know that the linear. I'll write it down like this. So, whoops. Phi such that the kernel of phi contains the image of T. These get sent to 0. These get sent to 0. Okay. And then you can show that ones that for which this is not true, those get sent to something non-zero. Okay. And so with this idea in mind, you realize, aha, things that get sent to something non-zero are things that send something non-zero in the image of T, that send something in the image of T to something non-zero. Okay. But yes, all of those linear functionals, right, they can be spanned by the they can be spanned by kind of vectors that are dual to basis vectors in here, right? And so, like, I'm just kind of trying to qualitatively explain the final result that we got, that the dimension of the image, I'll write it like that, that the dimension of the image of T is equal to the dimension of the image of T star. Okay? Right, so the image of T star, it is things that are non-zero over here that get sent to something non-zero starting at V. Okay? And it turns out that this happens in a one-to-one way if you look at it more carefully. Okay, this is the big thing that we proved. And from this, we can conclude that the row rank is equal to the column rank, right? Because we realized that in a very special kind of basis, the matrix for T and the matrix for T star in a closely associated basis is are just transposes of each other. Okay, so you know it's like the saying that the rank of a matrix is equal to, like, the column rank and the row rank are equal. It sounds like an easy thing to understand, but actually, you know, it's still fairly easy to understand. But it actually has something deep in that statement that says something about the dual space and not just T. Okay. Another comment that I want to kind of reiterate about the dual space is that everything that we have talked about so far really hinges on the fact that V is finite dimensional, right? If V is not finite dimensional, which is often the case in quantum mechanics, V is not isomorphic to V star always. And that is that's going to be kind of physically significant, because sometimes we will be searching for something in in quantum mechanics. We'll sometimes be searching for something in V, but it's not going to be in V because V is not going to be small enough. And so then we're going to say, well, what if we search for it in V star instead? Because we're going to have this bilinear form, which I talked about, or skew linear form. And there's going to be a way to put V inside of V star. Like there's going to be a natural way to put V inside of V star. And then you'll say, well, let's just think about V star instead of working with V. And then we will find the thing that we're searching for in V star. So yes, that is kind of a very vague foreshadowing of something that actually we might not even talk about. But this is something that happens in quantum mechanics, where sometimes you're searching for something in V, you can't find it, and so instead you search for it in V star and you find it there. And the way with which you're able to do the search is because you have a natural isomorphism from V to V star, you can just think of vectors in V as vectors in V star and just do everything nicely there. Okay, but that's kind of unrelated to this story with T star. That's just more about the previous comment about finding isomorphisms between V and V star. There's not always an isomorphism, but you will always have a mapping from V to V star. You'll always have an injective map from V to V star, but not always a injective and surjective one. Okay. Sorry, this was kind of a summary plus a bunch of other comments. Round of, I guess, virtual applause for Adam. Great presentation. It's very well put together. Sorry that we're online today. Hopefully we will be in person next week. Okay. Else I should have stopped the record. Actually, yeah, I'll stop the recording now.